this video, we are going to take a look at how to show that a piecewise defined function is differentiable. So in this example, we are given a piecewise defined function, h of x, with the rule that x squared plus 3x minus 10 is as long as x is greater than or equal to negative 3, and negative 3x minus 19 whenever x is less than negative 3. The goal is to show that this piecewise defined function is differentiable. Okay, well, if you look at the rules on their own, each piece of the piecewise function, those are very nice functions. For example, the first piece of this piecewise function is just a quadratic function. The graph of a quadratic function is a parabola. Parabolas are certainly both continuous and differentiable, so this piece itself is no problem. The second piece is maybe even easier to work with. The second piece is a linear function, and linear functions are also differentiable. So where, if any place, do we have to be concerned? Well, where we really need to be concerned is at the value of x where the two pieces are coming together, which is right here at negative 3. At negative 3, we aren't sure how the two pieces of the piecewise function are coming together, and we need to show that it's differentiable there. Okay, so to show that this function is going to be differentiable, we really need to show that is it differentiable at x equals negative 3. Is h of x differentiable at x equals negative 3? Alright, it will help to put down some steps for answering questions like this about piecewise defined functions. So here are some useful steps that can be used for any function. Then we will come back and use those steps on this example. So here are some steps. To show that a function f is differentiable at a given value, say x equals c, we'll do the following three things. Step 1. Show that the function is continuous at x equals c. Step 2. Find the derivative for f. Now you're not really finding the derivative for f at x equals c, since if you could do that, we would already know that it's differentiable. But we'll use our differentiation rules to find a possible derivative for f, and then we're going to check in step 3 to see if the limit as x approaches c from the left of that derivative is equal to the limit as x approaches c from the right for that derivative. The combination of these three do show that the function must be differentiable at that value of x. The third step is showing that the slopes of the tangent lines as we get close to C from the left are getting close to the same value as the slopes of the tangent lines as we get closer and closer to C from the right. Now, a curious student who is well on top of things might be concerned about how are we going to do step 1. So how is it that you show that a function f is continuous at a value of c? So to do that, let's put down some steps for that sub-problem. So to show that a function f is continuous at x equals c, we have to do the following 3 things. First of all, show that f is defined at c. That is, show that f of c is defined. There's no way a function can be continuous at c if it's not even defined at c. Step 2. Show that the limit as x approaches c of f of x exists. In practice, that means showing that the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. And then finally, the third step, we want to show that the value we got in 1 is the same as the value that we got in 2. Said another way, we need to show that the limit as x goes to c of f of x is equal to f evaluated at c. If these 3 conditions are satisfied, we can say that the function is continuous at x equals c. Then we need only find the derivative and show that the derivative is approaching the same value on both sides of c, and we'll know that it is, and then we will know that it is differentiable at x equals c. Okay, let's take it back now to the actual example that we were given and apply these steps. So that is a lot of steps, and if you need to pause the video, if you want to write them down, take a careful look at these. It may seem a little intimidating, but it is not so hard in practice. Let's apply these to the problem that we were given. Okay, so the goal here is to show that this piecewise function is differentiable at x equals -3, since we know that it will be differentiable everywhere else, since those are just nice polynomials everywhere else. It's only at x equals -3 that we might be worried. So let's do this. Step 1. We need to show that it's continuous. So let's show that h of x is continuous at x equals -3. First step. So first step for this is we need to show that h of -3 is defined. If x equals -3, go back to the piecewise defined function. If x equals -3, then we're using this first rule since it says that this is the rule to use when x is greater than or equal to negative 3. So h of negative 3 will be negative 3 squared plus 3 times negative 3 minus 10, which comes out to negative 3 squared is 9, plus 3 times negative 3 is negative 9, minus 10. 9 plus negative 9 is 0, minus 10 is negative 10. Negative 10 certainly is a value, so h of negative 3 is defined, and we've taken care of step 1. Step 2, we need to show that the limit as x approaches negative 3 from the left for h of x is the same as the limit as h approaches negative 3 from the right. So let's take them one at a time. The limit as x approaches negative 3 from the left of h of x, we have to decide which rule to use. If we're approaching negative 3 from the left, those will be values like negative 4, negative 3.5, negative 3.01, negative 3.001. So these are these values, so we're using the second rule. That will be negative 3 times negative 3 minus 19. So negative 3 times negative 3 is 9. 9 minus 19 gives us negative 10. So the limit as x approaches negative 3 from the left is negative 10. Let's find the limit as x approaches negative 3 from the right for h of x. If we're approaching negative 3 from the right, then we need to use the first rule, since those are values like negative 2.9, negative 2.99, negative 2.999. Those are values that are getting closer to negative 3 but coming from the right. Those are all values that are greater than negative 3, and so we need to use this first rule. So that will look like negative 3 squared plus 3 times negative 3 minus 10, which is going to be 9 plus negative 9 minus 10, which would be 9 plus negative 9 is 0, which is negative 10. This is very good, since now we know that the limit as x approaches 3 from both sides of h of x, this is as x approaches negative 3, from both sides of h of x is negative 10, since that was the limit from the left-hand side and from the right-hand side. We have this value. And now we just need to make the observation that, so that takes care of step 2, and now we need only make the observation that we just showed that the limit as x approaches negative 3 for this function is equal to this function evaluated at negative 3, since both of them turned out to be negative 10. Having done those 3 steps, we have now shown, so we can say, so h of x is continuous at x equals negative 3. By the way, that means it's continuous everywhere, since we know that it's continuous everywhere now, since we know that a parabola like this on its own is always continuous, And a line like this on its own is always continuous. The only place to worry about is where that parabola and that line are being glued together at x equals -3, and we show that it's continuous there also, therefore it's continuous everywhere. So now we need to finish off the differentiability. Let's take a look back here at the steps for showing that a function is differentiable at a certain value of x. First step for that is to show that the function is continuous there. We've done that. Now we need to find the derivative and show that the limit of that derivative is the same as we approach c from both sides. Okay, let's do that. So we need to find the derivative. We go over here where you can see the function, and let's find the derivative. Alright, so if h of x is given by this piecewise defined function, then finding the derivative is not so hard. The derivative of h of x will be, we just take the derivative of each piece. The derivative of x squared plus 3x minus 10 is 2x plus 3 when x is greater than or equal to -3. And the derivative of -3x minus 19 is just -3 when x is less than -3. Okay? So there we have we've now found the derivative. We can now use it we need to now show, so we've done first part, we've shown that h of x is continuous at x equals -3. We did that in the previous step. Step 2, we found h prime of x. We've taken care of that. And so now we just have to show that the limit as x approaches -3 from the left of this derivative is the same as the limit as x approaches -3 from the right for this derivative. Let's do that right here. So let's see, as x approaches -3 from the left, which rule do we use? If we're approaching -3 from the left, we need to use this rule, since those are values that are less than -3. But there it says the derivative is just a constant, and a constant will not change no matter how much x changes. And so we have that the limit as x approaches -3 from the left of the derivative of h of x equals -3. On the other hand, the limit as x approaches -3 from the right of the derivative of h of x, well, now we have to use this top rule because we're approaching -3 from the right, so we need to use values of x that are greater than -3. So that will be using that top rule, which is 2x plus 3 for the derivative. So that's going to be 2 times -3 plus 3, which is -6 plus 3, which is -3. This is very good, since this is what we got for as x approaches -3 from the left of the derivative was -3, as x approaches -3 from the right of this derivative is -3. That does show that those two limits are the same. And the combination of all of these allows us to conclude. So we say, so we have shown that this piecewise function h of x is continuous and differentiable. We've specifically shown that it's continuous and differentiable at x equals -3, but since we know that those functions, which define its pieces, are continuous and differentiable everywhere else, we've really shown that this function is continuous and differentiable everywhere.